Thank you, everyone. Good afternoon, first of all, and thanks for coming to our symposium series, coming to the Rising Star Talk and our symposium series. So we are a special introduced group from IEEE Communication Society, and our special interest in AI and machine learning in security. So our SIG is we are a few active members in our SIG. Our chair is Professor Suba from Stevens Institute of Technology, and myself, I'm Devashri Roy from UT Arlington, and Moinul is here today. He's from George Mason, and Hanif is from Rochester Institute of Technology. So our group has a presence, growing presence in LinkedIn, and we have many members, more than 600 members in LinkedIn. And we also have a website, which I'm going to show later. So please feel free to, if you are interested to get involved with our activities, please feel free to send us email. So far, what type of activities we have done? We have done since 2020 some virtual seminar series by different distinguished scholars all over the world, and it was virtual, like this talk as well. And all the talks, recorded talks, are available in the SIG website and also in our YouTube channel. And this talk will also make it available on the YouTube channel. So a little bit about our this Rising Star Symposium series. So this is a new initiative from our group. We are running it for last 1 year almost, or maybe a little bit more than 1 year. So it is an opportunity to hear from the rising stars of our community, like senior PhD students and postdoc, to present their work to an audience, or a virtual audience, and so that they can be prepared for their job talk and possibly interactively engage with the audience. So far, our rising stars had been, I think we had total 12 talks already, starting from 2023. And yeah, I think this is total 12 talks, and today is our talk for October 2025. And so a few things about the logistics of the talk. Everyone is muted on entry. We request them to stay muted. But please feel free to type in your question for the speaker in the chat box, and we will be moderating those questions at the end of the talk. So now I'm going to introduce our today's rising star, Ms. Afia Anjum. Afia is a PhD candidate in the Computer Science Department of University of Texas at Arlington. She also has affiliation at Los Alamos National Labs on project funded from Office of Cybersecurity, Energy, Emergency Response under the U.S. Department of Energy. And her research focuses on designing mechanisms that enhance efficiency, resilience, trust in wireless systems. She has numerous different publications in top venues, various transaction and journals. So with that, I will stop, and Afia, the floor is all yours.
Thank you, Dr. Roy, for this great introduction. Let me share my screen. Is the screen visible? Okay. So as Dr. Roy already mentioned, I'm Afia. I'm a PhD candidate in Computer Science Department of University of Texas, Arlington. And in parallel to my doctoral studies, I'm also working with Los Alamos National Laboratory. And the topic of today's talk is exposing vulnerabilities in text-driven semantic communication. We have already published a paper from this topic, which got published in IEEE CNS. So before I dive into semantic communication, let's first have a quick recap of the traditional wireless communication. So in traditional communication, every bit is treated equally. The goal is very simple here. Whatever we have at the transmitter side, we will be sending that to the receiver side exactly as it is. We don't get to choose what we are sending and what we are not sending. So as you can see, it's a very simplistic architecture of wireless communication. We have the source encoder, channel encoder, modulator, then the data goes through the propagation channel, then we have the decoders, and we get the original data. Now, what is a semantic communication? If you see the architecture, it might look similar to the previous one. But if you look closely, you can see on the transmitter side and the receiver side, we have two new modules. One is semantic encoder, one is semantic decoder. Now, the goal here is semantic encoder will selectively extract and transmit the essential information that's needed for the specific task at the receiver side. And semantic decoder will reconstruct that transmitted data into something which is well understood by the application at the receiver side. So in semantic communication, we are not sending everything, just like we were doing in traditional communication. Here, we are only sending the data that's required for the receiver end application to perform its task. So usually the semantic encoder and decoders are transformers or transformer-based large language models that we have currently. So what are the applications of semantic communication? Now, there can be many applications of semantic communication. Let me give you two examples. So let's imagine we have a user named Alice, and Alice is talking to ChatGPT. Now, Alice has this prompt: "Good morning, my name is Alice. I'm living currently in Arlington, Texas. Can you please tell me what's the weather outside?" Now, for ChatGPT to answer this question, what does it need? It needs the location and it needs the question. The other information, those are not relevant at all. It's not required to greet ChatGPT. It's not required for ChatGPT to know the name of the user. So what semantic encoder will do in this case, it will remove the redundant information and it will only extract the information that's required for ChatGPT to answer. And then it will send it over the air. Semantic decoder will reconstruct it to a proper sentence and will send it to ChatGPT. Now let's see another example. Here, the receiver end application is autonomous vehicle control system, which only takes task executable commands. Now, let's imagine in car, we have camera and the camera captured an image. Now, there is no point in sending that image to that autonomous vehicle control system, because the autonomous vehicle control system will only understand the commands. So what the semantic encoder will do in this case, it will just extract the essential information, which is here the traffic light is red. And then it will send over the air to the receiver, and semantic or through-wire and semantic decoder will reconstruct it to a task executable command. So it will basically generate a control signal that can trigger the braking system, and that is well understandable by the autonomous vehicle control system. So what can be the advantages of semantic communication? I believe by now you have already guessed the biggest advantage, which is the bandwidth efficiency. As we are not required to send everything from the sender side to the receiver, we can reduce the bandwidth wastage. Now, there can be other advantages as well. For example, let's imagine a multimodal application scenario where we need to translate a text to speech. Now, different text can have different emotions within it. For example, if we say, "What is wrong with you?" that sentence can mean a frustration. That sentence can also convey a concern for someone. So semantic encoder in this case can analyze the previous chats and can embed the emotion within the text, so that at the semantic decoder, it can generate the speech with the accurate tone and sentiment. There can be another advantage of semantic communication, which is intelligent error correction. So when we are transmitting a data, bits can get flipped, it can get corrupted. So instead of retransmitting the data again, the large language models, which are used as semantic decoder, can actually guess the word which got corrupted. We have masked language models which can guess a word which is missing within a sentence by seeing the context around that word. So semantic communication encoder and decoders can also be used as intelligent error correctors. Now, we have established the fact that semantic communication is very beneficial, but is it secure? Since semantic communication is relying on deep learning models, it's vulnerable to adversarial attacks. Now, the previous works who have worked on semantic communication's robustness, they have only performed adversarial attacks when it's image-based data transmission. So when I was reading one of those papers, I saw this particular line. Due to the discrete nature of text, it's impossible to add perturbation to the text without being noticed by humans. And then I thought it's kind of true. Like when you are trying to perturb image, random perturbation can cause changes in pixel, which can easily fool the receiver end application, which can cause misclassification, but it's very difficult for human eye to detect those perturbations. But if you do random perturbations to text, yes, maybe you can deceive the model, but it might be detectable to human eyes because it will produce garbage text, which won't make any sense. So then I thought, okay, since everyone is working with image-based transmission, let me focus on text-based adversarial attacks. Then I was looking into papers that are doing adversarial attacks in text domain. One thing I noticed when I was doing this paper, no one was focusing on text generation models. Everyone was trying to fool the text classifiers by doing some adversarial attacks on text transmission. So from all these analyses, I set my objective that I want to do adversarial attacks on text-based semantic communication. So my goal here is I want to generate targeted semantic noise, perturb the transmitted text in such a way that there is a subtle shift in the semantic, but we maintain the grammatical coherence and the fluency. And the constraints here are, we assume we have no prior knowledge of the architecture, model parameters, logics, or the gradients of the deep learning models that are used within that communication. Now for semantic encoder and decoder, we assumed these are large language model based, and the application at the receiver end, we are assuming it's LLM enabled chatbot. Now, the adversary goal is similar to my objective. I am the adversary here who is trying to attack the semantic communication. The adversary wants to alter the semantics of the transmitted text, but also want to maintain the contextual coherence and grammatical correctness, and wants to deceive both the user and the chatbot. Now, adversary's knowledge and capabilities, we are assuming here that adversary has the knowledge of the wireless communication channel. So we are assuming the adversary can intercept and decode the signal. We base our assumptions based on the literature that's already established that an adversary can intercept a signal by doing eavesdropping and jamming attacks. An adversary can decode the signal through side channel attacks. And while in some cases, if decryption is not possible, there are some papers who establish the fact that with large language models, now you can decrypt the signal to some extent. We also assume that the adversary has knowledge of the channel condition and the modulation techniques used because we already have the deep learning based classifiers and channel estimators. And we assume that the adversary would be able to inject the perturbed text before the user can retransmit the original one. While we give adversary full knowledge of the wireless communication channel, we restrict the adversary from the deep learning models. We assume that the adversary has no access to the deep learning models used. The adversary doesn't know anything about the model architecture or parameters or the gradients of the models used in that semantic communication. So for conducting the attack, we proposed the semantic perturbation generator. In short, we say SemPerGe. It has two modules. One is significant token marker and another one is perturbation generator. So before diving deep into the technical details of how we created that tool, let's see a simplified attack overview. So let's assume we have a user talking to an LLM-enabled chatbot. Now, user is asking question, and the semantic encoder at the user side reduce the redundancy, and summarize the question, which is something like this. What are the ways to control anxiety while driving? Now we assume there is an adversary who was able to intercept the signal, decode the signal, and send it to the significant token marker. Now the task of significant token marker here is to identify the significant words within the question, changing which might change the semantic of the question. So for example, here the significant token marker identified anxiety as the significant word and replaced it with a masked token. Now this will be sent to the perturbation generator, and the perturbation generator replaced the mask token or the anxiety with sleep. So you can see there is a subtle semantic shift, but the grammatical coherence is intact. The contextual coherence is also intact. We are still asking something about driving, but we changed the semantics. Now, when the adversary sends this to the chatbot responds by saying ways to control sleep while driving include consuming caffeine for temporary boost or listening to energetic music. Now, notice carefully, it's a wrong answer. The correct answer should have been ways to control anxiety while driving include practicing deep breathing, listening to calming music. So, when this wrong answer when the chatbot is trying to send this wrong answer, the semantic encoder at the chatbot's end will perform its duty. It will reduce the redundancies. So if you see, the answer itself contains the question. So we don't need the question. It's a wastage of bandwidth. So the semantic encoder will extract the answer and will send it to the user. Now, user's semantic decoder has the question that the user asked, has the answer that the chatbot sent, and it will reconstruct the answer before sending it to the user. So now the answer is ways to control anxiety while driving include consuming caffeine or listening to energetic music. Now, this is completely opposite of what the user was supposed to do. When you are in anxiety, if you are consuming caffeine, you might feel more anxiety and you might feel jitterish. So this might not feel harmful in this case, but imagine if it was a medical chatbot. User is asking questions about something and the chatbot is giving answers about something else, and user might take wrong medications. So that might create a life and death situation. So this is how vulnerable the semantic communication is in its current stage. Now, how did we create these two tools for doing the adversarial attack? As we said, the first phase is identifying the semantically significant tokens using the significant token marker. Now, to create the significant token marker phase, we used pre-trained transformer encoder. Now, transformer encoders, they have attention scores across each layers and attention heads. So we aggregated the attention scores of each word within the sentence in such a way that finally we can see which words within that sentence receive the highest attention. Now we further refined the selection process using a named entity recognition model, which is a NAR model. So NAR models are trained to identify specific unnamed entities within the sentence. For example, if you give a sentence to it, it can tell us which is a location, which is a person's name, which is an organization's name, or is it a medicine name, is it a disease name? So usually, all these entities are always the significant tokens within a sentence. So among the question, whichever words were identified by the NAR model, we amplified their attention scores. And finally, whichever words got the highest attention score, we selected those words and replaced it with a mask token. Now the second phase is generating the adversarial perturbation using a perturbation generator. So now it's time to replace that mask token with something which is contextually coherent but introduces a subtle semantic shift. So for that, we used pre-trained text-to-text generation model, and we fine-tuned using our own custom attack-specific dataset. Now, you might ask why we didn't use masked language model, because In the starting of my presentation, I said that masked language models have the capability to replace a masked word within a sentence. The problem with masked language models are that they replace the word with a synonym. In our case, we want any word but not the synonym, because the synonym won't introduce the subtle semantic shift. So this is why we had to use a pre-trained text-to-text generation model, which we fine-tuned later. So during the evaluation, as semantic encoder and decoder, we use GPT-4 API. So the definition of the semantic encoder and decoder here is to reduce the redundancy, and the GPT-4 API can do it easily. So we didn't spend time on building the semantic encoder and decoder from scratch. The perturbation target here is that we need to perturb the question that's being transmitted from the user to the chatbot. We use two datasets, web questions, which has around 6,000 question answer pairs. These are all the popular web questions that are available on the internet. And we also used a medical chatbot dataset, which contains around 260K realistic doctor-patient dialogues. All these datasets are available on Hugging Face. For creating the significant token marker, we used, for the web question dataset, we used the BERT model. And for the medical dataset, we used clinical BERT. So clinical BERT is just another version of the BERT, which was trained or fine-tuned on medical dataset. For the NER models, for web question, we used BERT-based NER, and for the medical one, we used medical NER. For medical dataset, we tried to use medical specific large language models so that it can easily understand the medical terminologies. For creating the perturbation generator, we use the FLAN T5 model. And as we mentioned, we fine-tuned the T5 model by creating our own custom ATAC-specific dataset that we created via ChatGPT. So there was a group of students who basically created that dataset. So they first did prompt engineering from an initial basic prompt. They created the best version of that prompt to create the final dataset. So the dataset is basically for each question, we are first identifying the significant tokens. And then we are telling the ChatGPT to give us 3 adversarial versions of that question. So for each question from that dataset, we have 3 adversarial versions of that question. The ChatGPT needs to replace that particular word with something which is contextually coherent, but is not a synonym. So for the perturbed questions, we also need to generate the perturbed answers, because eventually we need to test whether the attack worked or not. So for the web questions, we use GPT-4 to generate the questions for the adversarial, generate the answer for the adversarial questions. And for the medical dataset, we use the MediChat Llama for generating the answers. For evaluation metric, we used BLUE score and ROC score. So BLUE basically tells us how much the adversarial question is similar to the original one, and ROC tells us the opposite, how much the original question is similar to the adversarial one. So we basically use this 2 metric because we wanted to make sure our proposed tool does not change anything apart from those significant tokens. We also used a text expansion rate metric because we need to make sure that we don't increase the text length, because that nullifies the semantic communication purpose. And also when the adversary will try to send that adversarial question, it will take more time if we are increasing the length. We also tried to check the grammatical correctness, because now large language models are trained to detect adversarial text. If they see that a text is not grammatically perfect, they think it's an adversarial text and they trigger the defense mechanisms. And also we needed to make it stealthy to the human eye, so it needs to be grammatically correct. And then we also measured the attack success rate. So the attack success rate we measured by taking the embeddings of the adversarial answers and the original answers, and we tried to see, using cosine similarity, how similar are those 2 answers. Now we need to define a threshold. Beyond that threshold, we'll say attack was not successful, and below that threshold, we might say attack is successful. So with multiple samples, we did analysis, and these are the 3 examples from our analysis. If you see the first example, the actual question here is, what form of currency does Germany use? Now, the answer is Germany uses euro as its currency. Now, our proposed tool changed Germany to France. Now, fortunately or unfortunately, they both use the same currency. So the adversarial answer is also the same. So the attack was not successful. And you can see the semantic similarity score here is 1. And if you see the second example, here it changed Germany to Canada, which uses a different currency. So the semantic score here is 0.91. So from our analysis, we saw that if the semantic score is below 0.99, it is a successful attack. So we set our threshold. If the semantic similarity score is above 0.99, it was unsuccessful. If it's below 0.99, it's successful. Now, there are a few false positive cases. If you see the third example, it says, what form of currency does France use? It's the same answer as the original one, but a slightly rephrased version. So because we are using large language models, even if we set the temperature value 0, sometimes they rephrase the answer into different forms. So although both are giving us the same answer, the similarity score here is 0.89, but it's not a successful attack. It's basically saying the same thing in different language. So we had to manually check all these instances. We had few student groups who were manually checking this. So we made sure that we don't count these unsuccessful attacks as successful attacks. And for the baselines, we use these 4 baselines. As I mentioned earlier, that all the papers, they were trying to fool the text classifiers. So how these baselines actually perform the adversarial attacks is that they perturb the characters, they flip the characters, they add emojis, they replace with dictionary definitions. So this is how they are trying to do their adversarial attacks. Now, if you see the attack performance, for the blue and the rogue score, you can see the baselines achieved perfect 1, but ours is not achieving perfect 1. Although it's good, but it's not achieving perfect 1. So the reason here is that ours is using text generation models, and those are not using text generation models. So what our proposed tool is doing is that it's correcting the grammatical errors. So if you see the first example, the question, the dataset itself had some grammatical error. It was using did and wrote at the same time. So what our model did, it corrected the grammatical error and made it grammatically perfect sentence. So apart from the significant token, which is Thomas Jefferson here, it also changed another word, which is not impacting the attack, but making it more correct. And if you see the second example, it had please help, and the large language model in our case thought it's not required, so it just removed it. But it's also not affecting the attack performance. And this is why we are getting less blue and rogue score than the baselines. Now, if you see the text expansion rate, we are in the negative percentage because, as you saw, it removed please help. So it's trying to reduce the redundant phrases that are not required. But if you see the baselines, they are actually increasing the text length. And if you see the grammatical correctness, we are getting more than the baselines. Now you may ask why we are not getting 100%. It's because the dataset itself had so many grammatical errors. So if you check the grammatical correctness of the dataset, it's way below our achieved correctness. And if you see the attack success rate, you can see ours performed way better than the baselines. Now, if you see this example, you will realize why the baselines are performing so bad in this case. So if you see the first example, which is on the web question dataset, here the significant token was selected as Merit Oakland. And if you see SemPerGe, it changed it to something else. But the baselines, they selected deep as the significant token, and they are adding space, emojis, they are replacing it with synonyms, which is not being able to fool the text generation model. If you see the second example, here all the models chose height as the significant token. Ours replaced it with weight. But if you see the baselines, they are adding space, dictionary definitions, synonyms, which again is not being able to fool the text generation models. And this is why they are getting very bad accuracy score. Now, in over-the-air attack, timing is very critical. If our proposed model is not time efficient, then that might impact the overall attack accuracy. So we also tested the generation time of our model and the baselines, and the purple one is ours. You can see it's taking way less time than the baselines. The reason here is that the baselines, they assume they have access to the receiver end application. So they are trying to query the receiver end application again and again and changing their adversarial text. So this is why they are taking more time. But in our case, it's just the inference latency. We also tried to test whether the timing varies on the input length. As you can see, the purple one is ours, and it does not vary that much on the input length. In the previous experiments, we considered text generation model or a chatbot as the receiver end application, but we also wanted to see how does it perform when the receiver end application is actually a text classifier or sentiment classification model, because that's very popular in NLP domain. So we used 3 sentiment classification models, 2 Roberta-based and 1 BERT-based, and we used the benchmark dataset, the Stanford sentiment dataset. And you can see the results. It's almost similar. Although the baselines have improved their accuracy, but still ours is getting more than the baselines. The reason here is that, again, the baselines, they are adding just a space or emojis, or they are just replacing it with a synonym. Now, you might ask why the baselines are still performing bad. Because the baselines here are meant to fool the classification models. The reason here is that the baselines assume they always have access to the receiver end application. They know the architecture, they know the gradients of the receiver end application. But in our case, we are assuming they don't know anything about the receiver end application. They don't have access. They don't know the model architecture. So here we are using a dummy model for them. They might be able to fool the dummy model, but they are not able to fool the actual model. This is why they are getting less accuracy. We also performed a user study with 40 participants. So what we did, we gave them the original questions and we gave them the adversarial answers. We perturbed the original questions to adversarial questions, generated the adversarial answers. We gave them the original question and the adversarial answer and asked them, do you see any discrepancy here? They couldn't find much discrepancy, like 95% of them said that it shows that it's contextually correct, and they thought it is the correct answer for that question, although those were not the correct answers. Then we also gave them the adversarial questions and asked, can you find any grammatical error or any semantical error in that question? And more than 95% of them, they said it's grammatically correct, it's semantically correct. So that proves the stealthiness of the attack. Now, the work does not stop here, and it should not stop here, although we have published a paper in this work, but there are many interesting future directions that we can actually take. For example, in our work, we made some bold assumptions based on the current literature. We said that we assume that the adversary is able to intercept the signal, jam the signal, the adversary is able to decode the signal. We also said that we assume the adversary will be able to send the adversarial question to the receiver before the user can retransmit the original question. So we need to actually implement this end-to-end pipeline and see how in real time these wireless communication aspects affect the attack performance. Can the adversary actually send the adversarial question before the user can retransmit the original question. So that's a challenge, and we need to see that. Then we can take another direction. We can test in whether this attack is possible in multimodal communication. For example, when we are sending text, image, and other form of data together, and if the adversary only changes the text, does that matter? Because it also have the associated image with it. So we can have test on that. And another interesting direction is that if we replace that chatbot with a text summarization model, does that work? Because from my intuition in tech for text summarization models, you will be given long paragraphs and trying to identify the significant tokens that will cause a shift in that summary is actually difficult. So how can we solve that problem? That's an interesting future direction. And also we need to design defense mechanisms and verify whether those actually work. So this was the work that I wanted to present. The actual goal of this talk was that I wanted to establish that yes, semantic communication is very beneficial. It can make our vision of AI native communication true, but in its current stage, it's actually vulnerable, and we actually need to think of how we can make it robust. So thank you. If you have any questions, I'll try to answer.
Thank you for the presentation, Afia. So I do not see any question from the audience yet, but maybe I can start. So first, interesting presentation. This is not my area of research, but it is interesting to see that like this kind of vulnerabilities. So my question is about the threat model. So if you could go to the slide where you explain the threat model, that's step 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes, this one.
This one?
Yes, yeah. The proposed attack. So this particular one. So so in my mind, I was thinking about the threat model that it seems like a man in the middle kind of attack, right? So
Yes.
it's in the middle. So my first question is, I'm trying to understand that if it is actually man in the middle attack, why do we have the step 9? We are supposed to go through the man in the middle, right? So 8 and 9. So after 7, 8 and 9 should go through the interceptor in this case, if we have a man in the middle. Does it make sense?
So let me try to answer and see if that solves the concern. So here what is happening that the user is sending the question and the adversary is only trying to perturb that question and sending it to the chatbot. Now, chatbot finally will answer the question, and chatbot doesn't know that someone is in the middle. And chatbot, whatever question it's getting, it will send the answer directly to the user because the adversary has already changed the question. So the answer is also changed.
Yeah, so on that case, this is where I understand it. It's just, so if we have an adversary who can intercept the message that is coming from the source, it can also intercept the reply that is coming from the chatbot, right?
Yes.
So that is what I'm trying to understand, is that whether we need to have this step 8 and 9, because if we can intercept as a man in the middle, we can just send any bunch of text as a response right back to the source. Does it
Right,
make
I
sense?
understand what you're trying to say.
Right? I mean, it's just something to think about
Yes.
for the future. And one other thing is that, sorry, I'm taking a little bit more time.
No, please continue.
One other thing is that, so I think you mentioned about one of the issues with text-based perturbation is that it is easily detectable by human eye, right? So in this whole proposed attack, where do you think we have a human in the loop, except for the source? So where do we have a human where a human can actually see these kind of perturbations?
So for example, the user here, so my assumption is that the user here, when it's getting the answer, So if we perturb the question in such a way that ChatGPT or any chatbot sees that it doesn't make any sense, then
Okay.
while answering, it will also give you answer, the question doesn't make sense, or whatever you are saying, can you repeat? So
I
when
see.
that happens repeatedly, the user might be able to understand.
Okay. I think I get your point. So your
So the
goal
point
is
was, if we try to generate
Mhm.
something which is grammatically correct,
Mhm.
ChatGPT won't request for another question, or any GPT.
Okay. All right, that makes sense. Yeah. Thank you.
Thank you.
Um,
Thanks, Afia. Maybe I can ask a question if so. The LLMs you tried with Chat GPT-4 only, right? But
Uh, yes, the semantic encoder and decoder, those were GPT-4.
is it dependent on GPT-4, or it can the same encoder decoder would work with other LLMs?
No, it's not dependent on GPT-4. I just wanted something which can reduce the redundancy and just summarize the message.
Okay. And so about the wireless channel, right? You have a wireless channel. So did you consider any lossy channel, or what type of?
So in this project, we actually didn't consider any aspect of the wireless channel. It was purely on from step 3 to
Encoder and
step
decoder.
5, basically. Yes. So actually, we should implement the end-to-end pipeline and see how the wireless communication affect the attack success rate,
I see.
and see if it's real time or not.
I see. So this is more like a lossless channel you are thinking.
Yes.
Okay. Yeah, I think.
Hello, Afia. Can you hear me?
Yes, I can hear you.
Yeah, I have a very small question. Like, at some point you mentioned you are considering some semantic score, right?
Yes, attention.
Yeah, semantic score. You wrote something like that. The first thing I want to ask, like,
Okay, I am.
what is this semantic score? And that second thing is, you said if it is more than 99, it is like the what is that?
So
You
this
s-
semantics.
you set some threshold for the if it
Yes,
is the adversary or not.
yes.
Yeah. So how do you set that threshold specifically?
So the semantic score, how I'm calculating. For example, if you see the first example, here the original answer is Germany uses this and that, and the adversarial answer. So with BERT model, I'm trying to take the embeddings of the original answer and the adversarial answer, and I'm trying to see the cosine similarity score between them. So
Mhm.
BERT actually gives you this metric, cosine similarity metric, which
Yeah.
takes the embeddings of two sentences and tell you how similar are those. For example, here
Yeah.
the score is perfect one because it's exactly the same.
Mhm.
So, and for this case, you can see the score is 0.91 because it's not exactly the same. With cosine similarity, when we are measuring, it gave us 0.91. So we did more analysis with more samples, and we saw that when the answer is different version from the original answer, we actually get a semantic similarity score below 0.99. If it's above 0.99, it's sometimes the pronoun change or the article changes or something like that, but it's always the same answer. But if it's below 0.99, there is a shift between the answers. So from our analysis, we set the threshold that, okay, if it's more than 0.99, we assume that the attack was not successful because we couldn't change the answer much. But if it's below 0.99, we assume the attack was successful because the answer was changed to some extent.
Yeah, that makes sense. And I didn't follow all the presentation, but I have another question. You use the GPT-4 API for the encoder part of the
The
GPT-4
semantic
API?
encoder and decoder, yes.
Uh, okay, I'm confused between the BERT and the GPT-4. So you're using BERT for what and GPT-4 for what? Because I joined in the middle, maybe.
No, it's okay. Let me show you the slide here. Okay, so as you see, as semantic encoder and decoder, I'm using GPT-4, which is basically summarizing the questions and the answer and reconstructing it. And the BERT I used for creating the significant token marker, which is and from the BERT attention scores, I'm trying to identify which tokens are significant.
I understand. Because it's kind of you label the token, something like that.
Yes, so the tokens which are significant, I replace it with a mask token. And then you see the perturbation generator where I'm using the flan T5 that is trying to replace that token with something which is within the context, but will create a semantic shift.
Yeah, I understand. Yeah, thank you.
Maybe I can ask one more question. So it's not a question, actually, it's more about, I think, a comment. So I understand that the primary contribution is primarily in the LLM side, right? And not really in wireless or network side. And as in your future research direction, you already mentioned about it, that how to make the threat model more credible.
Yes.
So based on my experience and the way the threat model you have explained is that it is not exactly like a man-in-the-middle attack. It's more of a, so in wireless communication, we call something called overshadowing attack. So the idea of overshadowing attack is that, so let's say you're sending bits 1010. What can we do to at the receiver side to look like 1011? We just flip a bit, right? So I understand it's a very simple, you have text. It's not like flipping just one bit, a lot more. But it's just that I believe I'm just trying to think that how people will attack this work, right? So trying to play the devil's advocate role. Maybe you can spend some time and talk to your professor to find out that what kind of threat model, because man in the middle attack, that step 8 and 9 is questionable. If you have a man in the middle who has complete control over the session, then that man in the middle, you do not have to go through all these hoops, right?
Yes, I can just give an adversarial answer.
Yes. Yeah, just give an adversarial answer. So yeah, so that is what I was thinking is that, but that's completely fine. It's just you need to find a threat model that fits it. So the overshadow kind of attack is closest to it based on my experience. But then again, there's a lot of other things. It's not that easy. There's a integrity check. There's encryption. There's so many other things that goes on, whether it's wired or whether it's wireless. So yeah, so the threat model is something maybe in the future you can spend a little bit more time into to like improve this work.
Thank you for the suggestion. And yeah, it's true. And unless we actually implement it from the attacker side, we won't be able to actually know whether it's possible or not in real time.
Yes, yeah.
So we actually need to implement that.
Yeah, I think real time is the least of the concern. I mean, it's just that with computation, maybe you can somehow figure out a way to how to make it more real time. And in the case of text, though, text takes time, right?
Yes.
So that is actually, I think that gives you a buffer space. I think the most critical part from security perspective is to whether the threat model is credible. So I think from my perspective, I'm a cybersecurity person. So that's what I was trying to figure out, that whether it is actually doable.
Yeah. Thank you for the suggestion.
Yeah, sure. I don't see any more questions from the audience. Do you want to add anything, Afia, to your presentation?
I would just say that for the defense, if someone wants to explore that area, so all the transformers, they have like a CLS token, which actually gives you the context and the summary of the entire input sequence. So if somehow we can protect that CLS token and also send it with our communication, then maybe before generating the answers or before doing anything, we can verify the CLS token to first see whether whatever has been sent is accurate or not. And maybe from there, we can generate some defense mechanisms for this.
Okay. Yeah, thank you.
But yeah, overall, thank you so much for inviting me for this talk.
Yeah, thank you for accepting our invitation. So it's good to see work like this. I'm new to the semantic communication part, so I learned something new. All right, so with that, thanks everyone for attending this session. Best of luck to you, Afia.
Thank you so much.
Okay, yeah, take care.
Goodbye.